Hi everyone, welcome back to Dave's Math channel. I'm your host David Tare. I decided to make one more video on derivatives. This is a sub-series of my series on first year calculus. This is a very important topic known as implicit differentiation. I'm not specifically computing derivative of any function here, but it's a very useful tool when you're differentiating functions. So anyway, let's begin. So what do we mean by implicit differentiation? Well, this is a very useful technique when you have a complicated function, either given by a very complicated function, your formula where it's too complicated to compute the derivative, or maybe you don't even have an explicit formula for the function, but you have what's called an implicit formula. What this means is that you know if you're writing y equals f of x, you have an equation involving x and y. So you have another function, a function of two variables, if you like, involving both x and y, and remember that y is f of x. So then what you can do is you can differentiate the formula for this new function, if you want to call that capital F of f of y, you can calculate f prime of x and y, and then since that's equal to something else you're given, you can calculate the derivative of the right side as well, and that'll give you a formula involving y prime in terms of x and y. So it doesn't give you an explicit expression for the derivative of f of x, but it gives you an implicit one that involves both x and y, and often that's good enough because you only want to, say, compute the derivative of f of x at a given point. Maybe you wanted the slope of a curve at a given point. So anyway, that's kind of a mouthful. Let's just jump into some examples. I think what I said will become a lot clearer if I show you some examples. So let's first consider a circle, which is we're given a circle of radius 5, center of the origin, and I think you guys remember from high school that the equation of such a circle is x squared plus y squared equals 25, which is the square of the radius in this case. So that's the equation of our curve. And notice that we don't have an explicit formula for y in terms of x. And as a matter of fact, it's not even a function of x, it's a relation. Because there's actually two values of x for every value of y, except for the ones at the end point. But anyway, so we want to calculate the slope of this circle at the point P with coordinates 3, 4. And I think it's pretty easy to see that the point 3, 4 lies on this circle, because 3 squared plus 4 squared equals 5 squared, which is 25. 3, 4, 5 right triangle. It's an easy way to remember that. So anyway, how do we solve this problem? Well, what we do is we differentiate both sides of this equation 1 with respect to x. So let's do the left side first. So the derivative of x squared is easy. That's just 2x. And now we have to compute the derivative of y squared with respect to x. So we're actually going to have to use the chain rule here. So the way we do that, you can think of this as dy squared dx, which is really just dy squared dy times dy dx by the chain rule. And dy squared dy is just 2y, but then dy dx, that's just y prime. So you're going to get 2y y prime for the derivative of y squared. And then the right side is easy. 25 is a constant, so its derivative is 0. So we get equation 2. 2x plus 2y y prime equals 0. Well, this is an easy equation to solve for y prime with. You just do a little bit of algebra. When you do that, you find y prime, which is just another name for f prime of x, is equal to minus x over y. Well, this is nice because now we can just plug in the values of x and y for the point we're given, 3, 4, and we find if we plug that in, the slope at the point 3, 4 is equal to minus 3/4. So that takes care of this problem. Let's do a little bit more complicated example. Here's a case where we don't even have an explicit formula for f of x. We could have used the last one to come up with an explicit formula for f of x in terms of x, but we didn't have to here. But in this case, we can't even do that. We have this complicated equation y times the natural logarithm of y equals x plus 1. It turns out there is a special function known as the Weber function that we could use to write y explicitly in terms of x, but that's beyond the scope of what we're doing, and we don't even need it anyway. So now we want to calculate the slope again of this curve given by this complicated equation at this given point, e minus 1 comma e. Let's just first check to make sure that this point really is on this curve. So when x is e minus 1, x plus 1 is e, so the right side is equal to e. But then if y is e, then you have e times the natural logarithm of e. Well, the natural logarithm of e is just 1, so that's just e times 1, or e. So we do get equality, equals e. So this point is indeed on this curve, which is good. I should always check that. Anyway, so let's solve this the same way we did the last one. Again, we're writing y equals f of x, and now we want to differentiate once again both the left side and the right side of equation 4, and we have to use the product rule and the chain rule this time on the left side. So let's use the product rule first. Let's compute the derivative with respect to y of the product y times the natural logarithm of y. Well, I think you guys remember the product rule. You take, first you take the thing on the left, which is y, and then you take the derivative of log y with respect to y, which is 1 over y. So y times 1 over y, that's going to give you 1. And then for the second term, you get the derivative of the thing on the left, which is just 1. Derivative of y is 1, times log y. That's just log y. So altogether, you can get 1 plus log y for the derivative of the left side with respect to y. But remember, we want the derivative with respect to x, so we have to multiply the whole thing by dy dx, which is y prime. So that's the left side. 1 plus log y times y prime. And now the right side is easy. That's just the derivative with respect to x of x plus 1, and that's just equal to 1. So we get this new equation, equation 5, implicit equation for y prime. We get 1 plus log y quantity times y prime equals 1. Well, that's easy to solve. We just divide both sides by 1 plus log y. So you get y prime, which is just another name for f prime of x, is equal to 1 over 1 plus the natural logarithm of y. Okay, now the last thing we have to do is plug in the coordinates of the point we're given. And this time we only need y, so y is e. So we're going to get f prime of m, the slope we want, f prime of e minus 1, if you like, is equal to 1 over 1 plus the natural logarithm of e. Well, we know the natural logarithm of e is 1, so we're going to get 1 plus 1 in the denominator, which is 2. So our answer is 1/2. So that's how we do that. That's how we do implicit differentiation. Like I said, it's a very powerful tool in calculus, and you'll probably use it a lot. So anyway, that concludes my video. Thank you for watching. Long live math, and I'll see you guys next time. Bye.